This conference will now be recorded.
Hello everyone. Today we will discuss Helmholtz energy, which is another important state function just like Gibbs free energy. And then we'll also see the relationship between Gibbs free energy and this new state function Helmholtz energy and what is the difference between these two. And after that there will be third law of thermodynamics. Two laws we have already seen, first law and second law. Now we will discuss the third law and what is the significance, that is by applying third law how we can get some results. Okay, and there will be some problems also. So Helmholtz energy, in some books you can find that it is expressed by the letter F, but in this case we will use the letter capital A. Okay, now Gibbs free energy, that is denoted by capital G, that we have already seen in detail. And G, when we apply when the system is isothermal and closed with constant pressure, then only we apply Gibbs free energy. But suppose the condition is not at constant pressure, isothermal closed, that is fine, it is still there. Isothermal closed, constant pressure, then we apply G. But suppose now it is still isothermal closed, but it is not constant pressure. Instead of constant pressure, now the condition is different. Now the condition is constant volume. So when it is so, that is the condition is changed from constant pressure to volume, now we cannot use G and we will use this new state function, which is Helmholtz energy denoted by capital A. So this is the difference with G. Though IUPAC, that is full form is International Union of Pure and Applied Chemistry, officially refers to these two functions. Two functions means one is Gibbs free energy, which is G, another one is Helmholtz energy, that is capital A, respectively. But you can also see that in different textbook, different types of terms are used for the same state function, Gibbs free energy and Helmholtz energy. But the important point is when you can apply Gibbs energy, when the conditions are isothermal, closed and constant pressure. But if it is constant volume, keeping other conditions same, now it will be Helmholtz energy, not Gibbs energy. So A, it is basically equal to U minus Ts. Remember what we know about G? It is combination of H and PV. But now when we are talking about A, it is basically combination of U, T and S, internal energy, temperature and entropy. Now if we take del sign, del A, so when it is del A, then right hand side also it will be del U, and Ts as T and S multiplied, so it will be del S when T constant, and that is del Ts. How you can write it, that I am writing here. So del Ts, when we apply del over Ts, it will be first keep T constant and del S change in entropy, then keep S constant and change in temperature. But we are doing this for isothermal condition. That means change in temperature, this term will be 0. So ultimately del Ts, when you apply del over Ts, you are getting only T del S. So in the right hand side we are getting del U minus T del S. So here it is mentioned why we are doing so, because del T is 0. That is shown here already. Now in place of T del S, you can also write Q, because we know the relationship between del S and Q. Del S is equal to Q by T. That means Q should be equal to del S into T. So instead of writing T del S, now we have written Q, heat. So this is equation number 1. Helmholtz energy, change in Helmholtz energy, that is equal to change in internal energy minus Q. Keep it aside. Now from first law of thermodynamics, we know this relationship, right? Now W equal to del U minus Q. Now if we compare these two equations, right hand side same terms present, that means del A will be equal to W. So putting it in equation 1, now we are getting del A should be equal to W. And this is actually the maximum work done. And as it is work done by the system, we are considering specifically. So that is why there will be a minus sign. But minus sign you can also put it in the left hand side. In that case, it will be minus del A equal to W max. So Helmholtz free energy is considered as thermodynamic potential, which calculates the useful work obtainable from a closed thermodynamic system, provided these conditions are fulfilled. So it is constant temperature and volume, unlike Gibbs energy where we consider constant pressure. So this is the main difference between Helmholtz and Gibbs energy. So just like we have already derived in the previous class that change in G value minus del G, that is also equal to this same type of expression we have obtained. But that is when constant temperature and pressure. But now we are having the same type of expression between del A and W max. But now the conditions are different. Now the condition is constant volume, not pressure. So for such a system means constant temperature, volume, and closed system. Such a system, if we have the negative of the difference in this Helmholtz energy, that is minus del A, that is equal to maximum amount of work that we can extract from a thermodynamic process. But remember, these two conditions are fulfilled. So now we know what is Helmholtz energy. Next we will see the relationship between G and A. So this is one important state function. This is another important state function. Basically, G is more important. If we see from importance point of view, G is more important. And the reason behind it is that as in case of G, we consider constant P. But in this case, we consider constant V. But now most of the reactions, that is if you consider chemical reactions as example of any thermodynamic system, we know that we do under constant pressure condition, not constant volume condition. So that is the reason most of the cases, most of the chemical reaction as it is done under constant pressure. So G is having more applications. If you compare the application between G and A, which is having more applications, if that is for practical purpose, obviously G is having more applications, and that is it is more important. So let's see what is the relationship between these two. The two functions, first of all, G is equal to H minus Ts and A is equal to U minus Ts. So this is that is how we express these two. So Ts fine, but here it is enthalpy, here it is internal energy. Now suppose the temperature is constant, and under this case if we take del both sides, so it will be del H and S del T, but S del T is 0 because temperature is constant. So we are having from Ts we are having only T del S. So del G is equal to del H minus T del S. Now we also know that del H is equal to del U plus P del V, provided pressure is constant, because if pressure is not constant you cannot write it. It is pressure constant, and change in enthalpy is this term. So what we will do, instead of writing del H, now we have written del U plus P del V. Next, what we will do, now we are having this equation. Now this del U minus T del S, if we take together, it means what? This blue part that I have highlighted, it is basically equal to del A, because from this equation, if you take del both sides, it will be del A equal to del U minus T del S, because temperature is constant. So this equation now we can write in a different way. So see how we have written del G is equal to now del A plus P del V. So this part is equal to del A and rest of the part is P del V. and here it is written in bracket that del A is equal to del U minus T del S provided temperature is constant. So finally, this is the relationship between del G and del A. But we have just proved that del A is equal to minus W max. So just put it here. So finally, this negative sign is here, but if you take negative sign both side, left hand side, right hand side, there will be negative sign before del G, positive before W max, and negative sign here. So this is the relationship, that is relationship between del G and del A is like this, but you can also get these equations if you put in place of del A, if you put minus W max. So all these different expressions, they basically help us to during when we will solve any problem. Suppose del G value is given, P del V given, you just have to find out del A. So these relationships will help us to solve different types of problems. So Gibbs free energy is G and this is A. We will compare these two. Gibbs free energy is calculated for system under constant temperature and pressure. So this part is still common here, but now it is volume, not pressure. So this is the main difference between these two. Gibbs free energy is often used since it considered at constant pressure. So as I have already said, application of Gibbs free energy is more important because for most of the practical parts, that is chemical reactions basically, in chemistry obviously we'll consider chemical reactions. So, and most of them are operated under constant pressure condition but not volume condition. So that is why Helmholtz free energy is not much used because it considered at a under a constant volume condition. Fine. So these are the that is, if we compare G and A, we can find these are the two important points. Free energy change, that is change in G value, and equilibrium constant, K equilibrium. We will try to find out the relationship between these two. And the relationship is such that if you know the K equilibrium value, you can calculate del G and vice versa. In a reversible process, the system is in perfect equilibrium with its surroundings at all the times. Now for such equilibrium, if we consider any chemical reaction, the corresponding equilibrium constant is K equilibrium. Equilibrium constant in detail we can know, that is basically different chapter, equilibrium chapter. But right now just see this expression, that is equilibrium constant, which is basically, in short I am saying, suppose we have A moles of starting material, capital A, equilibrium sign, and we are getting P moles of, okay, B moles of capital B. So this is product and this is reactant. Now when it is equilibrium, under equilibrium condition, K equilibrium, how it is expressed, details you will learn it in another chapter, equilibrium. So it is concentration of product B. First we have to write, that is denominator numerator, if we consider, first you have to consider concentration of B. And here we have only one product. If it is more than one, suppose B moles of capital B, C moles of capital C, then you have to write the other product concentration also. But here we have, for simplicity, I have taken only one product, which is B. And as here coefficient is small b, so that will be in the power, divided by concentration of reactant. And here A moles of A, capital A, that means this is the coefficient. So here we will write in power K. So this is the expression of K equilibrium. For any reaction which is under equilibrium, you can write the equilibrium constant. Why it is constant? Because when equilibrium is reached, the concentration of product raised to the power its coefficient divided by concentration of reactant raised to the power its coefficient A. This value is always constant. So that is why it is K equilibrium. It is called as equilibrium constant. So we will see the relationship between K equilibrium and del G. So obviously we have to take a system which is in perfect equilibrium with its surroundings at all times. Now for such system, that is a reversible chemical reaction, it can proceed in either direction simultaneously. That means it is dynamic equilibrium. Dynamic equilibrium means A is moving towards B, B is moving towards A. This process is going on continuously. So that is, it is dynamic. It is not static equilibrium. It is dynamic equilibrium. But the point is, though they are moving in both direction, A is converted to B, B is converted to A, but this relationship, concentration of B to the power small b divided by concentration of to the A, this is always constant. But there is a dynamic equilibrium. So if this is so, this means that the reaction in both directions should proceed with negative del G, because we know when there is a spontaneous movement, it involves negative change in Gibbs free energy. So here what we are seeing, that it is under equilibrium and A is converted to B, B is also converted to A, both are occurring simultaneously because it is dynamic. That means in both directions it is negative del G, but that is actually not possible, right? How in both directions del G should be negative? It means as if in both directions it is spontaneous. So what to do when we have this type of situation? What we consider? We can consider that it is possible only if at equilibrium del G of a system is minimum. Fine. So suppose we have this type of reaction. So here it is very simple example I have given. Here you can see A moles of capital A plus B moles of capital B. These two are on the reactant side. Product side we have C moles of capital C. Another product is also there, D moles of capital D. See, if we consider this type of general equilibrium reaction, then the free energy change of the above reaction in any state, it is not standard state, suppose in any state del G, how it is related to standard free energy? Standard free energy means now there is a not sign. Okay, so del G naught and del G, the relationship between these two is RT ln Q. So Q means it is just like K equilibrium, that is here also, that is Q. How you will write? You will write concentration of D to the power small d, C to the power small a. Same type of expression. But when we use the letter capital Q, when the equilibrium is not yet reached, then you can write Q. Expression of Q and K equilibrium is same. But difference is here, equilibrium is still not reached. So under that condition, you can have this type of relationship between del G and del G naught. One is free energy change under any state, another one is free energy change under standard state. Now what we will do, this del G naught, it indicates that all reactants and products, obviously they are under standard state, and Q is called reaction quotient. And here I have already written the expression, but you can also define it. Q is reaction quotient and is defined as the ratio of concentration of the product to the concentration of the reactant. But see, when it is not yet reached the equilibrium condition, under that condition you can write Q. But once it has reached the equilibrium condition, you cannot write Q anymore. Now you have to write K subscript equilibrium. So when equilibrium is attained, now we have to consider del G, which is the free energy change under any state. That now you have to consider as 0 when equilibrium is reached. Because when equilibrium is reached, a reactant can be converted to product, and product can be converted to reactant. So both directions there is dynamic equilibrium, and it means that it should proceed negative del G both sides, but that is not possible. It is impossible. So that is why what we are considering, that when equilibrium is reached, now del G is minimum, and that minimum is actually 0. So when equilibrium is reached, del G, which is not Don't think it is free energy change at standard state. It is free energy change at any state. That is 0 when equilibrium is reached. And now the expression Q you can write in place of Q A equilibrium. So as this part is 0, that means del G naught is equal to minus RT ln. So we have not written Q, we have written K equilibrium. So this is very important relationship. If you know the value of all the terms in the right hand side, you can get the value of del G naught, or suppose you know the value of del G naught, K equilibrium, and R is constant, you can also find out what is the temperature. So here ln we have changed to logarithm, a base 10. Now it will be multiplied by 2.303. So either it is minus RT ln K equilibrium or minus 2.303 RT log K equilibrium. So when we will have any problem, should be careful whether it is ln or log what you are using, because if it is log it is 2.303, and if it is ln 2.303 it should not be there. And as we know that del G naught is equal to this relationship. So see here, enthalpy change is under standard state, entropy change is also under standard state. Now this expression is also equal to minus RT ln K equilibrium. So why this is also important? Because suppose any of these quantity is not known, T is known, del is known, right hand side also known, all the terms, then you can find del H naught. So that is any unknown quantities there and rest of the quantities unknown, we can find. So these are the important relationship. So free energy change at that is under standard state del G naught, that is related to K equilibrium by this relationship. And as del G naught is equal to del H naught minus T del S naught, so that should also be written equal to minus RT ln K equilibrium, or if you are writing log base 10, it should be multiplied by 2.303. Third law of thermodynamics. There are two laws we have seen, first law and second law. Now what is the importance of third law, that we will see now. As temperature of any system decreases, what happens? Just think from the point of view of atoms and molecules. So we now will consider some microscopic view, not macroscopic. So from atomic level or molecular level in any system, when temperature decreases, the atom and molecules, they also lose their energy and they approach their lowest energy point. By doing so, what happens? The atom and molecules, their kinetic energy obviously decreases, because directly there is a relationship between temperature and kinetic energy. When temperature decreases, kinetic energy decreases, and vice versa. So what happens? Now kinetic energy of the atoms and the molecules decreases, and hence their random motion also decreases. Okay, so gradually their movement will be slow as temperature is decreasing. So if we take the system, that is the example of water molecules in ice crystal. So suppose we have a crystal of ice. Now in ice crystal there is water molecules, because chemical composition is not changed, and as it is in solid form, crystal form, so the arrangement of water molecules are very they are in ordered condition. And as a result, as we know, entropy is the measure of randomness. So obviously now the entropy of the system is very low compared to liquid water. If you consider ice, it is solid. All the water molecules are ordered, so entropy will be low, very low. Now suppose this ice crystal, or if I say solid crystal, it is further cooled. Now what will happen? The remaining vibration of the molecules, even if there is slight vibration present in the water molecules that are held in the crystal lattice, it gets lower and they have very little disorder. And what will happen? Very small entropy. And in this way, gradually it will reach, that is when temperature is reached 0 Kelvin. We know 0 Kelvin in terms of degree centigrade, it is minus 273. So when the temperature is reaching 0 Kelvin or minus 273 degrees centigrade, what will happen? That is the minimum temperature we can achieve. Basically 0 Kelvin also under practical situation we cannot achieve. But theoretically, if we say that is the minimum temperature we can achieve, we cannot achieve any low temperature compared to this. Okay. So what will happen? At 0 Kelvin, theoretically all modes of motion stop. Why written theoretically? Because though we are saying this is the minimum temperature we can reach, but actually reaching 0 Kelvin is also very difficult. So only you can think in terms of theoretical concept. Okay. So that is why we are saying theoretically as 0 Kelvin is the minimum temperature we can achieve. So what will happen? As if this is a minimum temperature, that means now there is no motion left in the atoms and molecules of the solid. Here we have taken example ice crystal, not necessarily it is ice crystal, it may be any other solid. Important point is the solid that you have taken, the atoms and molecules, their motion absolutely stopped. Okay. So absolute zero is a temperature that an object can get arbitrarily close to, but is not attainable. So is unattainable. Okay. If I'm saying it is not, then it is unattainable. So it is unattainable. You cannot attain it. And a perfect single crystal is also an ideal. That means if this temperature we cannot attain, that means whatever we are saying in the previous statement, that at 0 Kelvin theoretically all modes of motion stops. So this statement, that also perfect single crystal, that is also ideal concept. So as you cannot attain 0 Kelvin or minus 273 degrees centigrade, that means this perfect single crystal, that is also ideal situation and cannot be achieved. And a perfect single crystal is also an ideal that cannot, sorry, it's two types. Fine. So when absolute zero is achieved, in terms of energy, if we consider the atoms and molecules of the crystal, they will now have lowest energy and no randomness is left in the particles. That means now we can consider as if the entropy is zero, because entropy is a measure of randomness. And now we are saying that theoretically all the motion stops, so no randomness is present. That means now we will consider this situation where the entropy is zero. So this is actually the absolute entropy. Until now we have always considered change in entropy. We have never talked about absolute entropy. Suppose there is state 1, there is state 2. We had never talked about S1, that is absolute value of entropy at state 1 or absolute value of entropy at state 2. That we have never talked about. We have always taken the difference, which is del S. But now we are talking about absolute value of entropy. And how we have reached this concept? Because now we have considered 0 Kelvin and now we are considering theoretically that all modes of motion stop. So randomness is no longer present. And as randomness is no longer present, so if you have any solid system at temperature 0 Kelvin, so you can say that at that temperature, absolute value of entropy is basically 0. Fine. Now, what is the significance of this law? To see in this picture, perfect crystal at 0 Kelvin, but if it is temperature is greater than 0 Kelvin, so there will be some randomness. See, it is not perfect orderly arrangement, but in this case it is perfectly ordered arrangement. Okay. So how we can state this third law? The entropy of a perfect crystal is 0 at a 0 Kelvin temperature or minus 273 degrees centigrade, and it is called absolute zero. So third law basically we are stating in terms of entropy. So two things are important: entropy, this perfect crystal, and temperature. Now the actual application of this law. Third law allows us to measure absolute values of entropy. See, Now simply S is written, it is not del S, it is not change in entropy, it is the actual value of entropy for a substance. So you can measure it at 0 Kelvin. So it is always 0 for any system. From thermal data alone. That means thermal data is enough if we want to know. Unlike enthalpy or internal energy change, that is enthalpy change is del H, internal energy change is del U. And so in case of enthalpy or internal energy, you cannot get the absolute values of H. Suppose for state 1 or 2, H1, H2, or state 1 and 2, internal energy U1, U2, that we cannot find. But unlike enthalpy and internal energy, it is possible to obtain absolute entropy, that is S, by measuring entropy change that occurs between the reference point of 0K, where it is 0, and suppose another temperature is 298. So you are basically measuring the entropy. One is suppose 298 Kelvin, that is 25 degrees centigrade, and you are also doing it at 0 Kelvin. So as this is always 0, that means the difference in entropy, that is the del S, that will directly give you the value at 25 degrees centigrade. Here we have taken 298 Kelvin or 25 degrees centigrade, but it may be any other temperature, 30 degree, 100 degree, 50 degree. So just we are taking the thermal data. You are measuring entropy at 0 Kelvin and at suppose 25 degree, and this is always 0. That means another 298 when you are taking, there is a value, but that we do not know. But when you will take the difference between these two, that difference will directly give you the value at 25 degrees centigrade, because, and that is possible, the difference is giving you the value at 25 degrees centigrade, the corresponding entropy. Why it is possible? Because one temperature, one point we have considered is value 0. So that is why as reference point S is 0. So compared to this reference point, you can take any temperature where you want to measure absolute entropy. So in this way, absolute entropy we can measure, but that is not possible for enthalpy or internal energy. That is, it is written unlike enthalpy or internal energy. So for a pure substance, this can be done by calculating the increment of heat required to bring the substance from 0K to the temperature of interest. So here our temperature of interest we have taken 25. You can take 30, 50, whatever. So you just have to calculate the increment of heat, because we know del S, how we write it. We write it like this. So you just need temperature and the increment in heat that is required to bring the substance from 0 to the temperature at which you want to measure absolute entropy. So then summing the ratios of Q by T, we can get the absolute value of entropy. But remember, this is possible only with perfect crystal, because this is applicable only for perfect crystal. If you have perfect crystal without any defect, then only you can say that it is having 0 entropy at 0 Kelvin. But suppose if there is some defects or imperfection at absolute, that is even at absolute 0, then obviously now the entropy, you cannot say it is equal to 0. Now it will be greater than 0. Fine. And one more important point, absolute entropy of a system or substance, it can never be negative, because the reference point, it is always giving you S equal to 0. So the temperature of interest where you want to measure, when you will take this, that is summing this ratio of Q by T, obviously it will always be positive. It is not negative, is not possible. So maximum entropy, that is absolute entropy, as we are considering 0 at 0 Kelvin, that is the minimum value possible. So negative value of absolute entropy not possible. Yes, del S is possible. That is del S negative, that is fine. Change in entropy. but absolute value of absolute entropy of a substance, that can never be negative. Fine. So now we will discuss problem, because all the topics that are present in this chapter is complete. So here we have a problem for a diatomic ideal gas. Diatomic, this information is important. Ideal gas in a closed system, which of the following plots does not correctly describe the relationship between various thermodynamic quantities? So various thermodynamic quantities, here we have Cp versus P. It is heat capacity at constant pressure, heat capacity at constant volume, in y-axis, T temperature in X, then internal energy X, y-axis versus T, and Cv versus V. So as it is mentioned diatomic, first of all, whether depending on monoatomic gas or diatomic gas, there are actually different values of Cp and Cv possible. So that we have to memorize. There is no other option. So basically, if it is monoatomic, Cv value is 3 by 2 R. But remember, for diatomic ideal gas, it is 5 by 2 R. And when Cv is 5 by 2 R, Cp is this value. Why? Because we know Cp minus Cv is equal to R. So Cv is 3 by 2. That means Cp should be equal to R plus Cv. That means R plus 5 by 2 R, which will give you 7 by 2 R. So that is why when you have diatomic gas, ideal gas, Cv is 5 by 2, Cp is always 7. Now we know that Cv obviously depends on temperature, but it is independent of V because it is at constant volume. And when it is Cv, it is constant pressure. So it should not depend on change in pressure. Now we have to choose that plot which is not correctly representing the relationship of the quantities that are present in y-axis and x-axis. Now Cp, it is independent of P, but here from the graph you can see it is increasing like this. There is a positive slope. It means what? When P is increasing, Cp is also increasing. Just take any point here. This is the corresponding value of Cp. This is the corresponding value of P. Take another point. This is the value of Cp. This is the value of P. That means, suppose this is P1, this is P2. So when you have increased the pressure from P1 to P2, Cp is also changing from this to this. So there is an increase in Cp, but that is not correct. So see, just in the first plot, you can understand that this is wrong. But why the other? That means the other three should be correct. Now the other three, let's check. Cv is dependent on T, and there is some change. What type of change is not important, but there is some change. That means you cannot say this is wrong. Then U versus T, there should be some relationship. Exactly what relationship, that is not so easy to predict, but there should be some change. So U versus T, it is okay. And Cv versus V, Cv is independent of V. That is correctly represented here. See, it is parallel to x-axis. That means in x-axis we have volume. So when you are increasing the volume, suppose you are taking a point here, corresponding volume is V1, you are taking another point where the corresponding volume is V2, but in both volume your Cv value is fixed at this point. That means Cv is not changing with volume. So this is also correct according to this relationship. So only the first one is not correct, and that is why this is the correct option. Fine. Two blocks of same metal. So suppose this is one block, this is another block. Same mass, but they are at temperature, same mass and at temperature T1 and T2. Okay, respectively, are brought in contact with each other. So initially they are not in contact, but now you are touching each other, they are in contact and allowed to attain thermal equilibrium pressure is constant. Under this condition, the change in entropy, that is, the change in entropy means del S, for this process that we have to find. Okay. Now, here final temperature, as you are bringing close T1 and T2. And it is true that we do not know whether T2 is greater than T1 or T1 is greater than T2, but you can do this assumption, or you can also do the reverse one. So just take any assumption, T2 is greater than T1, and final temperature, it will be average of these two temperatures, that is T1 plus T2 divided by 2, because initially individually it is at T1 temperature, another block is at T2, but when they are in contact, now the final temperature, it will be something in between. So if T2 is high, obviously gradually T2 will decrease and T1 will increase, and it will reach the final temperature like this. Now we know that change in entropy ds, that is equal to, basically it is Q by T. Okay, so Q by T, and in place of Q we can write Cp dt. That is the relationship between, because it is clearly mentioned here, constant pressure. So this amount of heat that is involved, whether absorbed or released, in whatever it is, irrespective of that, the relationship, it is Cp dt. Now it is in terms of d. So if we do integration both sides, now what will happen, this ds, it will change to del sign. There is some finite change, and here Cp we will consider as fixed value. So that is why now it is out of integration, and it will be like this, Cp, which is not included in integration, and this is initial temperature Ti, the two limits of temperature between which we will do the integration, Ti to Tf, and dt by T. Now 1 by T, if we do integration in this limit Ti to Tf, after integration it will be ln Tf by Ti. Cp is unchanged because it is constant. And left hand side ds, now it is basically here also it is integration. So it will be, if it is, that is entropy, if you consider S1 and S2 for this temperature, then it will be the del S. So ds is changed to del S, and del S is related to this. Now there are two blocks. Individually, if you consider, for the first block, temperature is T1. So for the first block, you can say Ti is as if T1, and another block Ti is T2. So Ti will be T1 for one block and Ti is equal to T2 for another block. But Tf is same. Tf is same for both the block, which is T1 plus T2 by 2. So next step, what we will do, we will add the two del S. So see, if you consider del S total, so for the first block Cp ln, so this part is basically Tf, this part is Ti, and for the second block again this part is Tf. So just put in place of Tf and Ti, just put these values. Tf is same for both, but initial temperature different. So you are adding these two quantities and just check, this part is basically common. Cp ln T1, Cp ln T1 plus T2 divided by 2. So if you basically, we have to, if you extend it, that is ln T1 plus T2, and as there is a, that is T1 plus T2 divided by 2T1, how we can write it? So Cp, it will be as it is, but it will be ln T1 plus T2 minus ln 2T1. So from this part also you will get ln T1 T2 and ln 2 T2. So finally, if you arrange, that is add all this, you will get finally this quantity, that is Cp ln T1 plus T2. There will be a square because this is 2 times present, and divided by 4 T1 T2. So here basically some steps are jumped, but if you write it properly stepwise, you will see you will reach this, and it is matching with option 1. Okay. So it is very close to this value. Here we have 2. So be very careful in which case it is properly written. It is option 1. So this problem, we have to think it in stepwise. This is also related to entropy. The entropy change associated with the conversion of 1 kg ice, which is at temperature 273 Kelvin, and you are converting to water vapor. From ice you are converting to the gaseous form, which is written as water vapor, and temperature is 383. Temperature is different, the phase is also different, right? One is solid 273, another one is gaseous 383. Some informations are given, that is some values are given. Specific heat of water, which is in when it is in liquid state, specific heat value given 4.2 kilojoule per Kelvin per kg. It is specific heat, so it is per unit mass per kg. And specific heat of water vapor 2 kilojoule per Kelvin per kg. So these are the informations given for specific heat for water, 2 different conditions, for liquid water, for vapor water. And one more information, heat of liquid water fusion. There will be water. So liquid water, heat of fusion. Heat of fusion means when you are changing it from ice to liquid form, then the heat of fusion that is involved, that is the amount of heat required for this phase transformation. And heat of vaporization. So heat of fusion is 334 kilojoule per kg. See here, no temperature is mentioned in the unit. That means it is occurring at constant temperature. 334 kilojoule per unit mass per kg, and heat of vaporization of water 2491 kilojoule per kg respectively. Some log values are also mentioned, log 273, log 373 and log 383. From this information you have to find the change in entropy associated with this conversion. So you are converting ice to water vapor. So first step, what we will do, we will write all the steps involved, because it is not a single step process. 4 to 5 steps are mentioned. That is one by one. First we have to understand, and then for each step we will calculate the entropy change, and finally for all the steps, whatever entropy change you have obtained, you have to add all of them. So see, you have started from ice. So this is ice, water, solid. First you are changing it to liquid, water, H2O, liquid. Okay. So now in this case temperature change will be involved. Next step, this is step 1. Step 2, liquid water, again liquid water. So what you are doing here, you are basically increasing the temperature. Phase is same. In step 1, temperature is changed and phase is not same. Sorry, temperature is fixed, phase is changed. But for the second step, temperature is fixed. Sorry, temperature we are increasing. This is a little confusing. So when we will actually see the expression, it will be clear. So here, as state is same, physical state same for both. That means here some temperature change is involved. In this case, no temperature change involved. Now come to the third step. Here also del S3, that is for the third step, it is entropy change is del S3, and in this case from liquid water we are converting to gaseous water. So here physical state is not same. From liquid you are now moving to gaseous form. Fine. So now we have to provide some heat, but remember here del T is equal to 0. Here also it is 0. There is no change in temperature. And finally from gas to gas, that means here also some temperature change involved in the fourth step. So total 4 steps are there. One by one we will calculate the entropies. But we have to understand first, when there is change in temperature involved, these two, and when there is no temperature change involved, two different expression for change in entropy you have to consider. So when it is fixed temperature, that is for step 1 and step 2, you have to use this formula, del S equal to del H transition by T. So here phase transition is occurring. See, from solid to liquid, from liquid to gas, only phase transition occurring. No temperature change. But when there is temperature change involved, that is 2, 1 and 3, and this is 2 and 4. When temperature change is involved, now phase is same, temperature is different. So in this case, del S is equal to number of moles. Capital C is heat capacity. So it may be C or S, depending on whether it, from the unit you have to understand whether it is specific heat or specific heat capacity given in the question or molar heat capacity given. From the unit you have to understand, and accordingly you can use the formula. So when it is molar heat capacity, number of moles multiplied by molar heat capacity, ln, final temperature by initial temperature. When it is specific heat as given in our case, see, it is per kg. Now you have to consider the mass, and mass is given 1 kg. So in place of m we will write 1 kg. S is given, so basically we have to use the second formula, not this one. That may happen, but you should know, you should have knowledge about this, all these formulas, so that you can apply according to informations given in the question. So del H transition by T we will apply it for one step and third step. So here N is number of moles, M is mass, everything is mentioned. C heat, specific heat capacity, sorry, it is molar heat capacity, and this is specific heat capacity, but we will use this, not N and C. So finally del S1, that is equal to this formula. So this formula you will use in these two cases, del S1 and del S3. Del H fusion value is given 334. Fusion means from solid to liquid, and for third step basically it is you are converting from liquid to gaseous form, and this is it will involve del H vaporization. So it is del H vaporization by T, which is equal to 2491 divided by this 373. Okay, so 2491, that is heat of vaporization. We will write it here in the denominator, it is 373. Okay, so we are getting these two values. Now come to del S2. In del S2 it is basically you are just changing the temperature, and you have to write 1 kg. So 1, it is not written, basically it is 1. 4.2, which is specific heat of water in liquid condition, 4.2. So it is liquid, so 4.2 ln, final temperature 363, and this is 273. So this is 273, this is 363, and after that we have del S4. So in del S4 we will use 2 kilojoule per kg per Kelvin, which is specific heat of water vapor, because in this case only vapor is involved, and final temperature is 383, and before 383 we have the temperature 373. This is 370. Sorry, it is not 373. Okay, 373. This is also 373. This is 373. That is initial temperature. 373 temperature is fixed, and this is 383. So final temperature, this is initial temperature for last step, and this is 0.05. Finally, what you have to do? Final step is, we have almost done everything. So you just have to add all these values. So if you add all these values, you will see, you will get this one, 9.26. Option 4 should be the correct option. Okay. So here applying two different formulas. This formula, which is for phase transition, temperature is fixed in this case. Another formula, which is for phase is same, temperature is different. So this we will use for second step and fourth step. This formula we will use for first step and third step. And finally, when you will add all this, you will get the actual answer, which is 9.26. So we are at the end of the session. Thank you for listening.